Good afternoon, class, and welcome to Chapter 9, Part 3. So when we left off, we were talking about concentrations and dilutions, and we had a formula that said that C1 times V1 equals C2 times V2. That's the formula we're going to be looking at using over the next few examples. And so example 12 says, what is the final concentration when a half a liter, right, units of liters, would be a measure of a volume, right? So we have liters here, which is a volume, of 6 molar hydrochloric acid solution, that's a concentration, is diluted to a final volume of 1 liter. So again, we have C1 V1 equals C2 V2. So our initial volume, our V1, is a half a liter. Our initial concentration is 6 molar equals C2, which we don't know, times V2, which is 1 liter. Okay, to get rid of the 1 liter, we divide both sides by it, right? And our liters cancel, leaving us with a final unit of volume, which is good since we are solving for a concentration. So 6 molar, 6.0 times a half a liter, 0.5, divided by 1 is 3. So our new concentration is 3 molar, which makes sense. We started with a half a liter and we doubled that to a full liter. So it makes sense that our concentration was halved. Okay, let's look at another one. What volume of a 2% mass by volume, this is a concentration, can be prepared by diluting 25 milliliters of a 14%. So we have a concentration, and it doesn't matter whether you call this C1 or C2. We'll call it C1. You have a V2 and a C2. So we have C1 V1 equals C2 V2. Okay. For C1, we have 2% times V1, which we don't know, equals our C2, which is 14%, times our V2, which is 25 milliliters. Dividing both sides by our 2% to get rid of it should get us a volume of, let's solve it here. Our percents are going to cancel, leaving us with a volume in milliliters. 14 times 25 divided by 2 gives us a new volume of 175 milliliters. 175 milliliters. And again, those units are in milliliters because the percents cancel, leaving us with only the unit of milliliters. If we wanted this in liters, we could have initially converted this into liters, or you could convert your final answer into liters. Okay, example 14. What is the percent mass by volume of a solution prepared by diluting 10 milliliters, this is a volume, of 9%, this is a concentration, to 60 milliliters, this is a volume. So we have a V1 and a V2, we have a C1. We want a concentration, so we're looking for a C2. So our V1 is 10 milliliters. Our C1 is 9%. Okay. Our V2 is 60 milliliters. And our C2 is, we don't know. That's what we're looking for. Oops, we don't want a percent sign there. We want a C2. Okay, let's draw that back again. C2. So to solve for C2, we would divide both sides by 60 milliliters. Okay, so we have 10 times 9 is 90, divided by 60 gives us a new concentration of 1.5%. And again, your concentration should be smaller because you're diluting, right? So if your concentration came out as more than 9%, you would know you had made a mistake somewhere. The other thing you want to keep an eye on are your units. In this case, we had milliliters and milliliters. But if you're doing your homework and they give you liters for one and milliliters for the other, make sure that you convert them so that you get the same set of units. You don't want to have liters on the top, milliliters on the bottom, because then they're not going to cancel. So keep an eye on your units. Otherwise, these are about as straightforward as they look. Okay, so let's talk about some basic properties of solutions now that we've done the math. Solutions are transparent, but that doesn't mean that they don't have color. And solutions can be colored, right? You just have to be able to see through them. A great example of this is Kool-Aid. If you make Kool-Aid, you can see through the bottle of Kool-Aid, but they have a color to it. They do not separate, and they contain small particles, ions, or molecules that cannot be filtered and pass through semi-permeable membranes. A great example of this is if you mix salt and water and then pour that through a filter. Nothing will be left behind, right? Because the salt is dissolved in the water and it goes right through the filter. So salt water is a solution. We also have something that we call colloids. Colloids have, instead of small particles, they have medium-sized particles. They also can't be filtered. However, the difference between a colloid and a solution is that they can be separated by a semi-permeable membrane. So again, colloids are similar to solutions, but their particles are a little bit bigger, and they can be separated by a semi-permeable membrane. Examples of colloids are like, for example, fog. Clouds are colloids. Hairsprays are colloids. Dust, smoke, right? Slightly larger particles, shaving cream. So there's lots of different colloids out there. And again, the key is just that they have medium-sized particles and they can be separated but cannot be filtered. And then finally we have suspensions. Suspensions are heterogeneous, meaning you can see differences, non-uniform mixtures. They have very large particles that settle out of solution. They're easily filtered, and you have to stir them in order for them to stay suspended. A great example of this is if you mix sand and water. If you don't continuously stir it, the sand will settle to the bottom. Muddy water, very similar, right? Calamine lotion, you ever notice before you use it, you got to shake it really well to mix everything up again? So a suspension is a mixture, but it's not a solution because if you don't continuously stir it, the things separate out. And they have very large particles. There's a nice little table here that shows you the three types, solution, colloid, and suspension. And it also shows you the differences. So you're going from small particles to larger as you go down the table. Particles do not settle for the first two, but settle rapidly by the time you get down to a suspension. And then the separation, right? A solution cannot be separated by filters or semi-permeable membranes. A colloid can be separated by semi-permeable membranes, but not filters. And a suspension can be separated by anything because they have large particles. Okay, let's talk about freezing point lowering and boiling point elevation. When you add a solute to water and it's no longer pure water, the physical properties change. And the vapor pressure above the solution decreases. This also means that the boiling point of the solution increases and the freezing point of the solution decreases. A great example that we use for this is in the northeast, which most of you are not familiar with. We have to add salt to the roads to prevent ice from forming. Which again probably doesn't happen much down here in Atlanta, but where I'm from, up in the Northeast, we do it pretty much all winter long. We have salt trucks that come salt the roads. These types of properties are called colligative properties, and it only depends on the concentration of the solute particles in the solution. So the amount that it lowers or raises the temperature, freezing point lowering or raising the boiling point, only depends on the concentration of the particles, not the types of particles. So it doesn't matter what you dissolve in the water, it matters how much you dissolve in the water. So when we talk about vapor pressure lowering, we're increasing the concentration of the solute particles in the solution, which decreases the number of solvent particles at the surface of the solution. Remember that the solvent is the thing present in the larger amount. This prevents some of the solvent particles from leaving the solution, which is why it increases the boiling point. A solute that is a non-electrolyte dissolves as molecules. Remember that a strong electrolyte breaks down into ions, right? So a strong electrolyte dissolves entirely as ions. And this is something we've talked about before. This is not a new concept. The non-electrolytes tend to come from our covalent compounds, and our strong electrolytes tend to come from our ionic compounds. The solute in antifreeze, which you put in your car, is ethylene glycol, and it is a non-electrolyte and dissolves as molecules in water. So 1 mole of ethylene glycol gives you 1 mole of particles. The solute sodium chloride, which is an ionic compound and a strong electrolyte, dissolves as ions in water. Once it's dissolved, you've gone from 1 mole of sodium chloride to 1 mole of sodium ions plus 1 mole of chlorine ions, which gives you a total of 2 moles of particles in solution. So a covalent compound, 1 mole of any covalent compound that does not dissolve it as ions gives you 1 mole of particles. However, when you dissolve an ionic compound, you generally get 2 or more moles of ions for every 1 mole of salt that you dissolve. Okay, so let's try an example of this. Now, in order to solve these problems, there are 2 values that are in your book that you will need to know. The first is that for every mole of particles, whether we're talking ions or molecules, for every mole of particles, the boiling point is increased by 0.51 degrees Celsius per mole, per 1 mole. And the freezing point is lowered by negative, or by 1.86, right, per mole. And again, it does not matter what types of particles. Okay, all particles added to water increase the boiling point by 0.51 degrees or decrease the freezing point by 1.86 degrees. So let's try an example. Let's see here. So we have a 1/2 mole of calcium chloride in 1 kilogram of water. And we want to calculate what the new freezing point is. So we have a 1/2 mole is our starting point. A 1/2 mole of calcium chloride. Now, we need to know how much the freezing point has decreased. However, in order to use this factor down here, we must first know how many moles of particles we have. Calcium chloride is an ionic compound. Therefore, it's going to break down into ions. We're going to have a calcium ion and 2 chlorine ions. Remember that calcium forms an ion, a cation, with a charge of +2. And chlorine forms an anion with a charge of -1. So we have 1 calcium and 2 chlorines for a total of 3 moles of particles for every 1 mole of calcium chloride. So 1 mole of calcium chloride has 3 moles of particles. Now we can use our factor over here that says that for every 1 mole of particles, the freezing point is decreased by 1.86 degrees Celsius. So let's see how much we've actually decreased the freezing point. So we started with a 1/2 mole times 3 for 1.5 times 1.86 tells us that we've decreased the freezing point by 2.79 degrees. The original freezing point of water is 0. 0 minus 2.79 in degrees Celsius, right, equals negative 2.79 degrees Celsius. So our new freezing point, we have decreased it by almost 3 degrees. Okay, let's talk about osmosis. You probably have heard the term used. In osmosis, water, the solvent, flows from a lower to a higher solute concentration, and the level of solution with the higher solute concentration rises. The concentrations of the 2 solutions will become equal with time as they even out. Osmotic pressure is the amount of pressure necessary to prevent that from happening, right? So we want to prevent the flow of additional water into the more concentrated solution. That is the osmotic pressure. How much pressure do you have to put onto this thing? As the number of dissolved particles in the solution increases, the osmotic pressure increases. So the osmotic pressure is greater as you increase the number of dissolved particles in your solution. In a process called reverse osmosis, you place a pressure greater than the osmotic pressure, forcing it through a purification membrane. So for example, if you want to purify seawater, right, if you tried to do this, the pure water would flow into the salt water, simply diluting it. Instead, you want the water that's in the salt water to flow the opposite direction. So you want the salt to be left behind, right? You've got your seawater here and your fresh water here, and they're separated by this membrane. You want to force the water through this membrane on this side, leaving the salt behind. So we have to place a pressure on this system to make this happen. This is used in desalination plants to observe pure water from salt water, but it requires a large amount of energy and isn't really cost effective. Cell membranes in our bodies are semi-permeable. So osmosis is an ongoing process that happens in your body on a daily basis. Water flows in and out of your cells depending on the concentration differences between your cell and the blood. In your body solutions, you have solutes, such as blood, tissue fluids, lymph, and plasma. These things all exert osmotic pressure. In fact, most IV solutions used in hospitals are isotonic solutions, which exert the same osmotic pressure as body fluids, such as red blood cells. This includes a 5% mass by volume glucose solution or a 0.9% mass by volume sodium chloride isotonic solution. You want an isotonic solution because you don't want the water flowing either out of your red blood cells or into your red blood cells. If the water flows out of your red blood cells, the blood cells become dehydrated in a process we call crenation, and they can shrink down. And if they lose too much water, they die. The opposite can also happen. In a hypotonic solution, the water flows from the solution into the red blood cell, causing it to swell. And you can see the difference in these two pictures here. These cells are much more swollen, and the little donut-shaped holes in the middle are much shallower. This is because the water has flown from the solution into the platelets. If enough water flows into your platelets, they can eventually burst. Eventually, they won't be able to hold the pressure anymore, and they burst. This is every bit as bad. So you want an isotonic solution, one which leaves the red blood cells as they are and doesn't cause the water to flow into or out of them. Not a hypotonic or a hypertonic. So again, a hypotonic solution has a lower solute concentration, meaning water flows into the cells by osmosis. The increase in fluid causes the cells to swell and eventually burst. This is something we call hemolysis. A hypertonic solution has a higher solute concentration than the red blood cells. So in this case, the water goes out of the cells by osmosis. This causes crenation, which causes the red blood cells to shrink in size. Again, if they shrink too much, they'll die. In dialysis, which is a common procedure you may have heard of, solvent and small solute particles pass through an artificial membrane. Large particles are retained inside. So this is something that we use when your kidneys aren't functioning properly. We use dialysis to kind of filter out the bad stuff and prevent you from making yourself sick. So waste particles such as urea from the blood are removed using hemodialysis, which is a name for an artificial kidney. Okay, so again, this is a process that we use to help people whose kidneys aren't functioning, and we treat it just as if the machine were a kidney, and it filters out the bad particles, leaving behind your fluids that you need to survive. And here's just a picture of how that looks. So during dialysis, the waste products and excess water are removed from the blood by a machine, and your clean blood is pumped back into you. So this concludes Chapter 9, Part 3. Thank you for listening, and I hope to see you for Chapter 10. Have a great day.